All right, let's just jump right in. For about a century now, physicists have been grappling with this really deep, kind of unsettling question. Is the very foundation of our reality imaginary?
It really all comes down to this, the Schrödinger equation. I mean, this is it. This is the master rulebook for the entire quantum world, and for 100 years it has worked flawlessly. But if you look close, right there, smack in the middle of it all is the letter I, the imaginary number. It's this, discomforting presence, as physicists have called it. A piece of what we thought was mathematical fiction sitting right at the heart of physical reality.
And that forces you to ask a pretty wild question, right? If the math that describes our universe perfectly needs an imaginary number to work, then what does that say about the universe itself? Is reality on some fundamental level imaginary?
To even begin to answer that, we first have to get to know this mysterious little character I that seems to be pulling all the strings in the quantum world.
So what even is I? Well, officially, it's the square root of -1. Now think about that. In the real world, you can't square any number, positive or negative, and get a negative result. A positive times a positive is positive. A negative times a negative is also positive. It's why René Descartes famously just called them imaginary, and, well, the name stuck.
And get this, even Erwin Schrödinger, the guy who came up with the equation, was uncomfortable with it. He really hoped that his version was just a rough draft, that someone soon would come along with a better, more real version that didn't need this imaginary fudge factor. But that never happened. Which leads to the next big question. Why did this mathematical ghost stick around? Well, because as weird as I is, it turned out to be incredibly, almost spookily, useful for describing how the quantum world actually behaves.
You see, I has this one very special superpower, rotation. If you take a number and you picture it as an arrow on a graph and you multiply it by I, it doesn't just get bigger or smaller. It literally rotates a perfect 90 degrees. And since quantum mechanics is all about waves and phases that are constantly shifting and turning, I was just the perfect tool for the job.
And as quantum theorist Bill Wooters puts it, this was a massive change. Before quantum physics, these complex numbers were, a neat trick for engineers and mathematicians. But with quantum theory, they weren't just a tool anymore. They seemed to be part of the very fabric of the theory itself, like nature was speaking in the language of complex numbers.
For decades, this was all just a fun debate for physicists. But then, in a totally brilliant move, scientists figured out a way to actually design an experiment to settle it. Could they prove, once and for all, that reality absolutely needs I?
I mean, just look at this timeline. This debate simmered for almost 100 years after Schrödinger wrote down his equation. It was pure philosophy. Then, bam, 2021. A team proposes a real-world test. By 2022, 2 different groups had done it. And the results? They looked like a total knockout. It seemed like the case was finally closed.
So how in the world did they test it? Well, it was a supercharged version of something called a Bell test. It involves entangled particles. These particles that are connected in a way that's, well, pretty weird, no matter how far apart they are. The researchers made this amazing prediction. If reality could get by with just real numbers, there'd be a hard cap, a speed limit on how strongly these particles could be connected. But if reality needed complex numbers, I and all, that limit would be higher. It gave them a clear, measurable difference to look for. And the results were incredible. The experiments found connections between the particles that blew right past the limit that a real number-only theory would allow. The data lined up perfectly with the version that used I. The conclusion felt rock solid. Quantum mechanics, and by extension, reality itself, has to have imaginary numbers. Case closed. But it wasn't. Just when the entire physics world thought this century-old mystery was finally put to bed, the story took a sharp, completely unexpected twist.
It turns out that amazing experiment, the one that seemed so airtight, was all resting on a single, very subtle, and as it turns out, very wrong assumption.
And here's what it was. The assumption was about a math rule called the tensor product. It's just how physicists have always combined the math for 2 separate particles. The experiment assumed that any real number theory would have to use the exact same combination rule. But that's kind of like saying that the rules for drawing a triangle on a flat piece of paper have to be the same for drawing a triangle on the curved surface of a globe. It's just not true.
So in 2025, the whole thing unraveled. 3 separate teams, one in Germany, one in France, and a researcher at Google, they all independently found the loophole. They figured out different ways to combine particles, different rules that let them build a complete quantum theory using only real numbers, and it made the exact same predictions. The proof was dead.
So, is that it? Is I finally kicked out of reality for good? Well, not exactly. The story gets even weirder, because even if you manage to push the imaginary number out the front door, its ghost seems to hang around in the math anyway. Here's the catch, and one of the physicists, Anton Trushechkin, put it perfectly. These new theories, the ones with only real numbers, they don't explicitly use I. But to get them to work, they have to invent all these new, complicated rules that basically force the real numbers to act just like complex numbers. In his words, they have to simulate I.
And this is the result. Yeah, the real number theories can work, but they are a complete mess, clunky, awkward, and just plain complicated. Instead of needing 4 complex numbers to describe 2 particles, you suddenly need 16 real ones. Meanwhile, the standard theory, the one with I, is simple, direct, and, well, beautiful.
And this takes us to a much deeper question, one that the philosopher of physics Jill North framed so well. Even if complex numbers aren't strictly necessary, the fact that using them makes the theory so much cleaner and more natural. It suggests that this formulation is particularly well suited for the job. It just fits.
So in the end, we're left with this incredible puzzle. We've learned that, technically, reality doesn't seem to require imaginary numbers to work, but it sure seems to prefer them. The language of I is just the most elegant, most powerful way we've found to describe the quantum world. And that leaves us with one last nagging question. If the imaginary math is the most natural way to describe the universe, what is reality trying to tell us about itself?